My name is Udit. I am here to present speeding up n matrix by 100x. So let's begin. So about me, I am a computer science student and a contributor to Ruby Science Foundation, also known as SciRuby. I've been part of the Google Summer of Code 2019 to work on the project called NumRuby, which is the topic of this whole talk. Then also we'll talk a little bit about Ruby Sparse. So yeah. So what's SciRuby? So SciRuby stands for Ruby Science Foundation. SciRuby has been trying to push Ruby for scientific computing. Most of the popular gems are like NMatrix, Daru, iRuby, RubyPlot, and RBCUDA. So NMatrix is the numerical core of SciRuby. It supports dense and two types of sparse matrices, which are linked list space and CSR. CSR stands for compressed sparse row. And then we also have linear algebra support, which is backed by Atlas, CBLAS, CLEPEC, and Standard LEPEC. Then we have Daru. Daru stands for data analysis in Ruby. Daru is basically pandas for Ruby. You can do a whole bunch of things with it, like you can analyze your data, visualize your data, manipulate it, and store it. It uses mainly two data structures, which are Daru data frame and Daru vector. Then comes the iRuby notebooks. You must have heard about the IPython project, which is also called the Jupyter project. So iRuby is the Ruby kernel for the Jupyter project. It's a browser-based REPL, which means that it's a browser-based interface to the Ruby interpreter. You can use iRuby with NMatrix and Daru to do a whole bunch of things with your data. Then comes the RubyPlot. RubyPlot started 2 years ago. Its aim is to be the complete plotting solution for all your plotting needs. It also aims to be flexible, extensible, and Ruby-like API. It currently supports the GR and RMagic backend. The RMagic is the Ruby wrapper to the ImageMagick library. Then comes the RBCUDA. So CUDA is used for GPU computing on NVIDIA GPUs. So RBCUDA supports on GPU numerical computing and linear algebra. It also comes with a CUDA profiler. Then let's talk about the n matrix, like how slow it is. So like first, like these are the benchmarks for n matrix versus NUMO and Ruby and NUMO NRA. So NUMO NRA is an alternative to n matrix, which is basically a dense library, dense matrix library, just like n matrix. So as you can clearly see, like the lower one is the better one, which is NUMO in this case. So it completely outperforms n matrix. These are for the matrix addition, which is the element-wise addition operation. Then comes the element-wise subtraction, similar case, like completely outperforming. Then is the matrix dot product, same case. So like what was the reason behind it? So the n matrix, which started in like 2011, was written by a bunch of people, each one having different implementation for their backend. So like some part was written in C, some was in C++, some was purely in Ruby. So like when we combined those and made the interface between them, so it kind of made slow because like we have to convert the data like while transferring from one backend to the another. Also like the development of NMatrix wasn't focused primarily on performance. So NumRuby. So NumRuby started last year in November. It's a completely from scratch re-implementation of NMatrix. So its aim is to like match the speed of NumPy, which is the similar library in Python, and NUMO NRA. So like how does it do that? How's its solution? So NumRuby has been written completely as a clean and simple code, so that makes it easy to change and like find issues and like extend and improve. Also, you'll see the benchmarks that its speed actually matches NUMO NRA and even outperforms in some of them. So it does also support indexing, iteration, and slicing. Slicing wasn't like also the part of NMatrix earlier, so it's part of NumRuby now. Then like here's the benchmarks for NumRuby versus NUMO. As you can clearly see that the difference is pretty small here. Also, this is the first iteration of the implementation, so like we can further improve it to even make it even better later. So then this is for the subtraction, also quite similar. Like in some cases NMatrix is better, some cases like NUMO is better. So then is the multiplication. This is like the difference is like hardly visible, as you can clearly see. Here's the matrix determinant operation. Also, you can see the darker line is the n matrix. So you can see that the darker one is below the lighter one. So like it's a little bit better than this. Then comes the matrix factorization. So matrix factorization is basically to break down the matrix, which could be like SVD decomposition or could be the QR decomposition. This case is the QR decomposition. So as you can clearly see for the elements, if the number of elements is 25 million, then you have like 7 seconds for NumRuby and 14.7 seconds for NUMO. So yeah, if you want to do factorization and want to save like 7 seconds of time, you know what to do. Then let's take a look at like how NumRuby works internally. So first off, we have written the backend completely in C, and it's been implemented using the standard Ruby C extensions API. And the n-dimensional matrix is stored as a row major one-dimensional array. It's because that it will make all the internal operation pretty simple to do. Then, like there was a major issue using just a C was that we can't use polymorphism because obviously it's not a OOPS language. So one hacky solution was to use the switch statement. What that does is that if you want to have like 4 data types, so you have to write the same code 4 times but with different data types. So that's kind of hacky, but like it works. So like, yeah, we're looking for a better alternative, but like for the time being, this works. So like we're going with this. Then here's a simple struct in C for the n matrix. So first is the data type, which could be float, int, or complex. Then comes the S type of the matrix, which could be either sparse or dense. Then the sparse is now not supported in NumRuby. It's been taken out, and it's in a different library called Ruby Sparse, which I'll explain later. Then comes nDims, which is the number of dimensions. So if you have a 2D matrix, the number of dimension is 2. If you have a 1D array, then the number of dimension is 1. Then comes the shape of the matrix, which is the length of the row, length of the column, or length of the any other dimension that you define. Then comes the sparse struct, which is also, first, then comes the pointer to the elements array. So it's pointer to the memory location where all the elements are stored. Then comes the pointer to the sparse struct, which is also depreciated because like it's part of Ruby Sparse now. Then, we have element-wise operations. So like we do support addition, subtraction, product division, logarithmic, and trigonometric operations. We also are working on the user-defined operations, which is like you can just define a function, which will take the 2 values and perform some operation of them and return a value C. Then you can pass that function on to the user-defined operation method, and it will perform the element-wise operation using that function on both the matrices. So then comes the indexing. So as I told you earlier that the n-dimensional matrix is stored as a 1D array in the backend. The n-dimensional matrix is indexed using a tuple of length n. And the one-dimensional matrix, one-dimensional array that's stored in the backend, its index has just a single value. So there needs to be a mechanism to convert this n-dimensional n-length tuple to that value. So for that, we use strides. I'll explain an example what stride is, and then I'll explain the mathematics behind it. And you can also do iteration along the row, along the column, or any other dimension that you want. You can also do the iteration with indices. Then, then comes strides. So what's a stride? A stride stores the starting index of each dimension. For an n-dimensional matrix, stride is also a tuple of length n. So like to calculate, you just pairwise multiply the tuple, index tuple with the stride tuple, and add those values to get the single value index. So here's an example. So first, like suppose we have a 3D matrix of 2 rows, 3 columns, and 4 layers. So a stride would work like you start from the right, you'll place 1, and then you'll place that value 4, and then you'll multiply by 3. So like that'll give you 12, 4, and 1. So suppose you have an index of 0, 1, 2, like you want to find what's the element as first row and second column and third layer. So what you'll do is that you'll multiply the index tuple pairwise with the stride tuple. That would be 12 into 0 plus 4 into 1 plus 1 into 2, which will give you 6, which is the 7th element in the one-dimensional array that's stored in the backend. So here, next comes broadcasting. Broadcasting is when, like, obviously for if you want to do element-wise operation, the two matrices needs to be of exactly same shape. But sometimes, like, the shape isn't exactly the same, but like they are kind of compatible. Like, if you want to perform some kind of transformation on an image, so like if you want to perform some kind of mask, so that could be a 1D vector on a 2D matrix. So in that way, if the one of the dimension is equal, then they are compatible using broadcasting. So here's an example of which two arrays are compatible using broadcasting, which are not. So the first one is like a 2D matrix with 2 rows and 3 columns, and then have a one-dimensional matrix of length, one-dimensional array of length 3. So for broadcasting, what you do is that first you take this smaller shape, which is the lower one having length 1. You prepend that one with ones until they become equal. So we'll prepend just 1, 1 here. So they'll become 2, 3, and 1, 3. Then you'll pairwise compare, like if they are equal, then we'll take that value. If they're unequal, one of them needs to be 1, or they are not compatible. So in first case, like you'll have 3, 3, then you have 2, 1. So the final resulting array, the matrix become 2, 3 shape. Similarly, for the second case, 5, 3, 4, and 3, 4, that becomes 5, 3, 4, 1, 3, 4, and the resulting one is 5, 3, 4. But for the last case, you can see that it's incompatible, because if this will transform to 2, 3, and 1, 4, and then 4 and 3 are unequal, so like it's incompatible even with broadcasting. So next comes the linear algebra. For linear algebra, most of like nearly every numerical computing library uses BLAS and LAPACK, which are like highly optimized Fortran libraries for these purposes. So NumRuby also uses these libraries. So we have written a wrapper called NumRuby LAPACK, which is a wrapper to the LAPACK library, and this wrapper is further used by the NumRuby linear algebra to form the linear algebra operations. So what were the challenges faced during this whole process of 1 year of building this library? So first, the major issue with N-matrix was obviously the multiple copying of data, which was slowing it down. So we had to decrease that copy of data. Then we have tried so far to reduce as much as we could. Also, we are tracking down to further decrease it. So another issue was to handle large matrices. So one example could be like if you have a large enough matrix that can't fit in your memory, so like you'll have to have a mechanism to get that to working. So then also the API needs to be simple to use. So what we did was that we used some inspirations from NumPy, some inspirations from Nuvo, and some we thought would be the best, and like created the best possible solution that we could. Here's a simple example of the usage. So like first you require NumRuby, and then you create a simple N matrix. So here in this example, it's a 2D matrix with 2 rows and 2 columns. So this example is in the iRuby notebook. So like then you can perform n plus n, which will give you the answer. Then you can also get the determinant of this matrix by performing n dot det. Then here's another example. So here in this case, you have you first define one matrix and then another matrix M. Then first one, n into M, is the pairwise product. It'll element-wise product each element. And then suppose if you want to perform the dot product, then you can write n dot dot M. So it'll give you the dot product of the two matrices. So this is all, obviously, like there's still time left. So I guess not. So like there's, yeah. So here comes Ruby sparse. So Ruby sparse is special because like for n matrix, you had NUMO, which was much a better solution. Or you can also, like in Ruby, go with NUMO if you don't want to go with n matrix. But for the sparse matrices, you don't have an alternative right now, which is like you do have a couple of libraries, but they are not complete. They're like just weekend projects kind of stuff. So this library was started a month ago, and we aim to like make it a complete sparse solution for all your sparse needs. So it currently aims to support these 4 types of sparse matrices, which is compressed sparse row, compressed sparse column, and coordinateless and diagonal. Also, there is a need for an easy conversion between the dense matrices. So obviously, we have implemented the interface to N matrix and NUMA N array. So you can easily use those libraries with this one. Then what's a sparse matrix? So a sparse matrix is nothing but like a matrix with too many zeros. So if too many zeros, it doesn't make any sense to store all the zeros. You can just store the non-zero values and save your memory too much, and like also like it'll become faster in some of the operations. So here's a simple struct for that. It's quite similar to the earlier one. So like first we have the number of dimensions, then you have the count of number of elements we have. So in this case, it'll only store the number of non-zero elements. So this is the count of number of non-zero elements that the matrix has. So next comes the shape of the matrix. Then next comes the pointer to the elements array. And then there's also like two other pointers which are the pointer to the, so like suppose like this is for the COO matrix. The COO works like, suppose you have a 2D matrix. So if you want to store only the non-zero values, what you will do is that for each of the non-zero value, you'll take the value and corresponding row index and the column index. So suppose you have a value 3 on the second row and third column. So you'll store 3, 2, 3, which is 3 value and second row and third column. So I and J are the row index and the column index. So what are the objectives of Ruby sparse? So its objective is firstly to be the complete library for sparse matrices. Also, it should be easy to be interfaced with dense matrices libraries. And it obviously needs to be fast. So this also has been written completely with the C backend using the Ruby C API. And it should also have an API that is very easy to use. So here's an example for that. So first we take an, yeah. So first we declare an CO matrix with 3 into 3 shape, and it has 3 elements. So like the first element is the first array is 1, 2, 3, which is the array for the element values. Then the second array is for the row indices, and third array is for the column indices. So what that transforms into is like the first non-zero element is having value 1 with first row and first column, and the second value is having value 2 and is on the second row and second column, and third value is 3 with on third row and third column. So if you want to find the shape, you can do n.shape, n.elements, n.coordinates. It'll give you the coordinates of the elements. So like, and then if you want to perform the element-wise operation, you can similarly do that. N plus n, it will give you the elements and coordinates. So currently, as you can clearly see, that if we print the array, if we print the sparse matrix, it prints the object fingerprint, not the exact values. So that's also we are working on to improve the iRuby support for this. Then here's a conversion for to and from n matrix. So like first we take from n matrix to COO. So first you declare a simple n matrix. So here's it printed. Then if you want to convert it to a COO matrix, you can simply do COO dot from n matrix and then pass the corresponding matrix. It will give you the corresponding COO matrix for that. So here are the values for that. Then next comes the reverse one. So you declare a COO matrix, and then you can convert it to n matrix. So you can see that this is also the same matrix which I used earlier in this in the earlier slide. So it's the diagonal matrix with only the diagonal values non-zero. And then here's the conversion for NUMO. Pretty similar. First you declare the n array, which is this one. Then you can convert it to the COO from like the class method using COO dot from n array, and then you can just convert the reverse one, which is from the COO to n array. So you declare a COO n matrix and then just write the corresponding, like in this case, n1 is a COO n matrix, so you just pass COO n1 dot to n array. So it'll give you the n array corresponding object, which is in this case, it's from m1 to m. Yeah. So we also have two other submodules for this sparse library, which is Ruby sparse graph and Ruby sparse linear algebra. So like for graphs, a graph is basically a set of nodes and edges and a set of relation between them. So like suppose you wanna like you wanna like in the maps and like the graph is also used in like many places, like for maps or finding the shortest path, or like maybe to find relations between certain objects. So to do some graph theory algorithms, you can use the sparse library, because like to represent a graph, a graph can be represented using a 2D matrix, and many of times what happens is that the matrix turns out to be sparse one. So for that, the sparse library can be used. So here are a bunch of the graph algorithms that we are going to implement. So first is depth first search and breadth first search. The shortest path is finding the path from point A to point B, and then comes the maximum flow, and then the minimum spanning tree. So we are planning to implement these and a bunch of others soon enough. And then comes the linear algebra module. So for the linear algebra, we did have BLAS and LAPEC for the dense matrices, but we don't have those for the sparse matrices. So like there are like possible two solutions for that. One is to like use some C libraries for that, and other is to write them by hand in C. So like we are currently discussing to use either of those or maybe like a hybrid of those. So yeah. And then what's the future work for the library? First is obviously to improve the iRuby support for the library, both of them, the Ruby sparse and NumRuby. And then the NumRuby linear algebra is kind of like halfway through. It's not complete yet. So we are going to complete that, and hopefully like it will be complete by the end of this year. And also like we are going to add the image processing support and the serialization support. Serialization is basically that if you have some, if you take some matrix and do a bunch of operations, then you want to store it in your drive, like in a file or something. So you need serialization for that. So currently it's not there. It will be like added by within next upcoming 6 months or so. And then yeah, so you can find me on GitHub, Twitter, or here's my blog. So yeah, thank you. So contributors are welcome. Both of these projects are open source. So you can find SciRuby projects on this link. And thank you. So thanks to GSOC and SciRuby for giving me this opportunity to work on these projects and to present them here. Thank you.